സർവശക്തനായ ദൈവം മനുഷ്യനായി പിറന്ന ആ ദിവസങ്ങളെ ഞങ്ങൾ ഓർക്കുകയും അത് ഞങ്ങളുടെ ജീവിതത്തിന് അനുഗ്രഹമായി തീരുകയും ചെയ്തുകൊണ്ടിരിക്കുന്ന ഈ ദിവസം വീണ്ടും ഇതാ ഒരു പുതിയ സെഷൻ. ഞങ്ങൾ കേൾക്കാത്ത കാര്യങ്ങൾ, കാണാത്ത കാര്യങ്ങൾ, ചിന്തിക്കാത്ത കാര്യങ്ങളെയൊക്കെ കേൾപ്പിക്കുവാനും പഠിപ്പിക്കുവാനും ഡോക്ടർ വിനോദ് സ്കറിയ ഞങ്ങളുടെ ഇടയിലേക്ക് അങ്ങ് അയച്ചു നന്ദി സ്തോത്രം അർപ്പിക്കുന്നു. ഇനിയും ഇവിടെ നടക്കുവാൻ പോകുന്ന ഈ സെഷൻ അത് എത്ര സമയമാണെങ്കിലും അത് ഞങ്ങളുടെ ഓരോരുത്തരുടെയും പേഴ്സണൽ ജീവിതത്തിന്, ഞങ്ങളുടെ ഇൻസ്റ്റിറ്റ്യൂഷന്, വരും തലമുറയ്ക്ക് വലിയൊരു അനുഗ്രഹമാക്കി തീർക്കണമേ. പലപ്പോഴും ഞങ്ങൾ പുതിയ കാര്യങ്ങളിങ്ങനെ കേൾക്കുവാൻ ഞങ്ങൾക്ക് കിട്ടുന്ന ഓപ്പർച്യൂണിറ്റിക്കായി നന്ദി. പ്രത്യേകിച്ച് ഡോക്ടർ വിനോദിനെ ഞങ്ങളുടെ മധ്യത്തിലേക്ക് അങ്ങ് അയച്ചു, അതിന് ഞങ്ങൾ സ്തോത്രം അർപ്പിക്കുന്നു. അടുത്ത നിമിഷങ്ങൾ അഥവാ അടുത്ത മണിക്കൂറുകൾ അവിടുത്തെ കരങ്ങളിലേക്ക് തരുന്നു. ഞങ്ങളോട് സംസാരിച്ചാട്ടെ, അവിടുത്തെ ദാസനെ ഉപയോഗിച്ചാട്ടെ. പ്രാർത്ഥനയുടനായി സ്തോത്രം. ഞങ്ങളുടെ കർത്താവും ഞങ്ങളുടെ രക്ഷിതാവുമായ യേശു ക്രിസ്തുവിൻ്റെ വിലയേറിയ നാമത്തിൽ തന്നെ ആമേൻ. പ്ലീസ് ബി സീറ്റഡ്.
Thank you, Achan. Thank you all for coming, and it's a real great privilege for us to have Dr. Vinod with us for today's quest. So we've been working with Dr. Vinod and his lab as part of our clinical work in hematology, and recently I was we just wrote up a proposal, and I had to get his CV. So it'll be a great injustice for me to talk about his CV right now. He has a Wikipedia page for himself. He has a genetic screen for himself. He is unofficially or officially called as the Genome Man of India. So I think we've benefited greatly from our interactions with him. And the difference that we felt with him is that we can talk to them about the clinical profile of the patient, and our reports don't have to be dogmatic that it has to be in this particular. So we've gone back, revised reports, and helped patients. So initially we were very skeptical that does it make an impact in clinical practice, but now by default all our patients, every sample will go through his screen because it is giving us multiple inputs. Instead of sending one test to multiple labs, I think if you interact with him, more doors will open up for many of the tests that you're already doing. And so many of you bright minds are already here, and if we interact with him, I'm sure more avenues will open up. And now that we are recognized as a reasonably good center here, we should elevate ourselves to the top of the research world. And I think I'll welcome Dr. Vinod. Thank you again for accepting the invitation to come. Anytime he says he's anywhere nearby, I think I'm not going to miss that opportunity to welcome him again. Thank you. Thanks.
Thank you, Dr. Chepsi, for inviting me again here. I think all that we started is almost from a similar talk almost a year ago, just over a year ago. And we have come a long way from just a discussion and just a talk into sort of probably building one of the largest cohorts in hemato-oncology in this part of the world, if not the country. And yeah, looking forward to actually having more interactions and more patients benefiting from genomics. Now, the next 40 odd minutes, what I'll try to delve is how genomics is moving the needle for precision medicine. And of course, there are very different varieties of precision medicine, or very different views of precision medicine and what precision medicine is, what it is going to impact patients, and so on and so forth. But largely my talk is going to deal with a bit of past, what happened in the past and what was genomics used in the past. What is genomics being used presently, and with a glimpse of what is probably genomics going to be used in the future, and what are the implications in a clinical setting when genomics moves the needle, and I'll talk about the needle and where the needle is today. Now, to give a brief overview of what I'm going to talk and where I'm going to start, and I'm not sure many people appreciate, I'm sure a lot of people can recognize what that equipment is. Can anybody guess what that is? Right, that's a CT scanner. The CT scanner was invented almost 50 years ago, and I'm sure today it is part and parcel of clinical practice. You cannot run a hospital today without a CT scanner. Even a decent-sized hospital of 100-150 beds needs to have a CT scanner. Now, why is that become so part and parcel is just because of the fact that 50 years ago, the only way a clinician could peek into the human body was essentially open it up, right? Exploratory laparotomy, and people used to die because of an exploratory laparotomy. people don't die today because a clinician wants to peek into the body. They can just send it to a CT scanner and actually peek inside the human body. Now, 50 years, it has become something that is very routine, largely because of the fact that technology has made it at scale, made it affordable and accessible to patients, and therefore clinicians can use it. Now, why I brought this up is largely because of the fact that 20 years ago, not 50, 20 years ago, we have an ability to peek inside, not just the human body, peek inside every single cell of the human body. There are 37 trillion odd cells, and today we have an ability to peek inside the blueprint of the human cell, and that is the genome. And they started with, of course, the first human genome announced in 2003. That's approximately over 20 years now. And what really happened in the last 20 years is largely the cost reduction and improvement in throughput that has happened in genomics. To put things into perspective, what you see here is in the log order, not even the linear order. And this would roughly mean that the cost of genome sequencing is becoming half every approximately 200 odd days. Now, the dotted line out there is the Moore's law, which is essentially the law of semiconductor industry, which essentially states that the capacity of the semiconductor doubles every 200 odd days. And you have a technology in biology today which is even surpassing the Moore's law in its ability. Now, what would this mean? This would largely mean that we are in a very interesting point in time in the history of medicine or genomics, where the cost of genomic sequencing is becoming affordable to be used in a routine clinical setting. Like today we use CT scanners in a routine clinical setting. The cost of genomics is becoming almost equivalent to that. And in fact, if the cost reduction is going to continue in the future, we think that it is going to go even beyond that. And that is essentially the premise of my talk today. Now, we were not really far behind in sequencing the first genome. We were actually the 7th country to be able to sequence our genome, exactly to be around 15 odd years ago. I was fortunate to be in the team to be able to sequence this. And we didn't really stop with one Indian sequence, but we actually went ahead to sequence many genomes in this part of the world, including the first Sri Lankan, the first Malaysian, the first Philippines. We were one of the founding partners of the Pan-Asian Population Genomics Initiative. And very recently, before I left IGIB, we were also part of the Middle Eastern large-scale population genomics initiatives. And today we have databases which also catalogs this entire landscape from Middle East to Southern and Southeast Asia, which essentially is a population migration region which sort of forms entire Asia. And we have very good insights into what genetic landscapes of the people in this part of the world are. Now, obviously, the question is not about sequencing genomes, because we have proven that we can sequence not just in India, but also collaborate quite extensively across the world. The question is, what do we do with these sequences, or how do we really impact patients? And one of the ways we started impacting patients is through a program that we started way back in 2015 with my colleague Sridhar, which we call as Guardian. Guardian is short for Genomics for Understanding Rare Disease India Alliance Network. The idea of this program is very simple. We will work with clinicians who see patients with undiagnosed familial rare genetic disorders. And at that point in time, we had this idea of rare genetic disorders. We don't think that is applicable anymore, because now we know that many of these rare genetic disorders are indeed very prevalent in the population. I'll come to that. So over almost 7 years, we built it from one single center, one single clinician, to today almost around 300 odd clinical centers, clinicians from around 70 odd centers, and impacting in the last count close to around 10,000 odd patients with extremely rare undiagnosed genetic diseases. And what we typically do is we work with the clinician, we do a standardized way of consenting, sampling, sequencing, and analysis. And whenever we get a pathogenic mutation, we get back to the clinician to say that, no, I think we have a solution to your problem. This is a mutation that causes the disease. That doesn't happen in all the cases. Approximately 50% of the cases that does happen. In the rest 50% of the cases, we do step back into the lab to create that additional evidence that is required to prove that the mutation indeed is what caused the disease. And by doing this over and over again, we have sort of made it into a sort of systematic pathway that any disease, any clinician from anywhere in the country could now participate into a very standardized process of looking at a genetic condition and be able to assess and ascertain what is the genetic mutation, what causes the disease. Now, I'll just give you one example on what we really do to just give a glimpse of how this is impactful. Now, this is one of the first families when we took it as a formal program in 2015, and that's a news clipping out there. This is a family who petitioned the President of India to euthanize 6 out of their 8 children. And those are the 6 children. The youngest and the oldest are not there in the picture. They're the middle 6 children. And what they have is a very progressive neurological disorder in the clockwise direction from the youngest to the oldest. They're perfectly normal at birth. They're perfectly normal at around 3.5 to 4 years. And eventually at 3.5 to 4 years, as the history goes, they go to school and they deteriorate in their milestones and eventually end up in a vegetative state. And one after another, 6 children with an undiagnosed, possibly genetic condition, and the family has no clue on what to do with this. They have gone to every major center across the country, and nobody has a diagnosis and nobody has a treatment. And out of frustration, the family petitioned the president to euthanize their 6 children because they don't have a hope. Now think of the plight of the family who will want to euthanize their own children because they have no hope, right? And I'll not say this is a very common thing, but this is also not very uncommon. Now, since euthanasia is not permitted in India, it came through official channels to figure out what is really wrong with these children. So what we did was to do a genomic analysis of all the 6 children. We figured out that it's an extremely rare genetic condition called cystic megalencephaly. I'm sure if they are neurologists in here, it is a short form of megalencephalic leukoencephalopathy with subcortical cyst type 2, an extremely rare genetic disorder with a prevalence of approximately 1 in 1.5 million odd by the global estimates. Now, of course, if it's such a rare condition, then the obvious question is, why do this family has this condition? Now, we visited this family over many visits. What we realized is that this family comes from a consanguineous community, what we call as an Alband community. The history goes that they came into India from modern Middle East, the Mediterranean basin, and they came with the invaders because they had a very unique skill of making horseshoes. And since they came with the invaders, they resided in parts of Agra, Aligarh, and Jaipur. And they formed a small community, what they call as an Alband community. And that really excited us. So what we did was to go around the community. There were 50,000 odd people in the community. We went around the community asking for whether you have another child with a similar condition, or can you also give us 5 mm of blood. Now we did this for around 100 odd families, and what we found was even more remarkable. So what you see in the pie chart is the number of affected individuals, number of carriers, and the normal people. Now I said before that this is an extremely rare genetic condition with 1 in 1.5 million prevalence. What we show is that we could find another 3 children in the community with the exact same disease and the exact same genetic event. And what we also show is that 28% of that entire community were carriers for this genetic condition. And what this number would translate is 1 in around 400 odd children born into this community would have this genetic disease. So now suddenly an extremely rare genetic disorder elsewhere in the world has become a public health problem in a small community in India. The advantage being that we all know who this community are. We all know what is the geographical or the cultural boundary of this community. And with a 1 in 400 kind of a genetic prevalence of a disease, not a carrier, what would necessarily mean that people need to be counseled, right? They need to be told that you are probably carriers of a genetic disease, you could test for it, and you can plan your reproductive decisions accordingly. It's not to tell that you should not marry or you should marry, but once you have married, you have an option to go ahead with your reproductive decisions. And there are now technologies to sort of look at it, prevent such diseases from occurring. So from 2016, from the first case referral to the diagnosis to the publication to today a diagnostic in the market, this is now widely available in the market. It's called the MLC1 Wandernap and Alband mutations. These are the 2 founder mutations in India. The first was called the Wandernap mutation in the Bansal Agarwal community, discovered out of All India Institute of Medical Sciences, and the second from the Nalband community that we sort of contributed. And this test today is approximately around 1,000 odd rupees, widely available, accessible in the community. Anybody who wants to have a carrier screen can today get it. Anybody who wants to get a diagnosis can also get it. So what I'm trying to say is that while we think about rare quote unquote genetic diseases, we must always keep in mind that rare or the estimates of rarity is essentially from global literature. They might have nothing to do with reality on the ground. And in many cases, such genetic conditions are extremely prevalent in communities. And to put numbers, India has around 4,000 such endogamous communities who marry within the same caste, tribe, religion, or whatever group of individuals. And in genetics, this is a gold mine because no other population in the world has large endogamous communities who marry among themselves. It also becomes a unique opportunity to identify genetic diseases and also implement genetic in practice, because you pretty much know that from your surname what community you come from, what is the probability of having the disease, and also if you were to intervene and have a public health program, you pretty much know which is the regions that you want to do a public health program. You don't need to spread your button really thin and think that something will hit somewhere. So this is just one example. So we have many such examples, probably like 30, 40 such examples. We have sort of compiled it into a publication with around 280 odd authors sometime in 2019, sort of telling this is their experience of doing such a program, not just in terms of research. Of course, research and publications are part and parcel of doing research, but how do we convert this into an educational program, into offering diagnosis to patients at scale, in terms of generating data for public health implementation, which is really, really important, because publication is one part of it, but the publication should actually benefit patients at the end of the day. And to benefit patients at the end of the day, you need to provide the data so that politicians can act upon it. At the end of the day, policy is made by politicians. Unfortunately, today, many of the diseases that today we have in the rare disease policy of the country actually came from this large project, because for the first time in India, we sort of made people understand that these are genetic diseases which are extremely prevalent in communities, so that you could act upon it. Many of them are indeed treatable. So you can have a policy to sort of go back and treat it. I'll discuss one more case to sort of highlight another problem on the multi-testing in a clinical setting. Now, this was a child we call Ashi. Of course, it's a pseudonym for the original name. This patient came to us from the All India Institute of Medical Sciences. The parents had 3 abortions in the past and early neonatal deaths in the past. And this child came with a very classical symptom of a mitochondrial genetic disorder with elevated lactate pyruvate and with a microcephaly with a high Nijmegen score. So clinician says and vouches that this is a mitochondrial genetic disorder. So typically what do you do in such case? You sequence the mitochondria. So apart from the nuclear genome, you have a small genome, 16,000 base pairs, which is a mitochondrial genome, which is inherited from the mother to the child. It's unilaterally sort of inherited. So we did the mitochondrial sequencing. We were the only center at that point in time doing mitochondrial sequencing in India. So we did it, and we didn't find anything, right? Which is not very unnatural. A clinician vouches for a gene, we don't get it. That is pretty normal. But then the clinician was very vehement that this is a mitochondrial genetic disorder, right? So when you exhaust the mitochondria, what you typically do is to do the next best test, which today is a whole exome sequencing. The idea of doing a whole exome sequencing is that a lot of mitochondrial genetic disorders are caused by nuclear genes which are translocate to the mitochondria. So the genes are in the nuclear genome, but the protein is made and translocates to the mitochondria. We did an exome sequencing. We did get nothing. In most cases, this is the end of the story, right? The clinician has given up, we have given up, and he says something will happen someday. But in this particular case, the clinician was even more vehement, right? That this is indeed a mitochondrial genetic disorder. So we said, okay, fine, if you really think so, we should really go back and look at. So what we did was to do a whole genome sequence. And whole genome sequencing was just coming into mainstream. This is sometime in 2017. We did a whole genome sequencing and we found the mutation. Right? The mutation was very simple. The father and mother had 2 heterozygous deletions, and the child has a compound heterozygous deletion with an overlapping region of around 140 odd kilobases, which encompasses exomes of through genes, and that was homozygous deletion. I'll just show this. So what you have in the child is this deletion. The father and mother has 2 heterozygous deletions. That means of the 2 copies of the chromosome, 1 copy is deleted. Part of that 1 copy is deleted. So in the child, we have as a common region and two heterozygous deletions for each of the two alleles from each of the two parents. And it overlaps a very important gene in mitochondrial biogenesis. So we know that it's a mitochondrial genetic disorder. So we sort of confirm that this indeed is a mutation that caused the disease. Of course, there's a lot of experiments that went behind it. And of course, the family will come back 9 months, 10 months, 12 months later with another pregnancy, asking what should we do with it. So we do a CVS, we do a whole genome sequencing, we prove that the child also has a disease or don't have the disease. Now, of course, after 6 more attempts, this family today has 3 apparently normal children, right? Now, this is really the power of genomics, that you can give hope to patients who have otherwise lost hope. That you can identify a genetic condition if, of course, the clinician is very persistent about what his or her diagnosis is. You can get to the solution to a problem if all 3 partners work together. And 3 partners, of course, one is a patient, the second is a clinician, and the third is the lab which can sort of implement such kind of a test. Now, of course, having said that, what I'm trying to also say is that while a considerable amount of time in this family was lost doing multiple different tests, almost they lost 1.5, 2 years trying to do multiple different kinds of tests. Today we have an opportunity to consolidate this into one single test, which is called a whole genome sequencing, which is increasingly becoming affordable. And of course, there are multiple studies which have shown that a whole genome sequencing gives much better diagnostic positivity than standard of care testing. Standard of care testing today is a panel testing or a whole exome sequencing. And even within our hands, we have been able to do that. So in summary, what I'm trying to say is that today in genetics, we use different kinds of tests. On one end of the spectrum, you use chromosomal karyotyping, FISH, to look at large chromosomal abnormalities, which are tens of thousands of base pairs. You use PCR-based approaches. You use MLPA for deletions. You use panel sequencing or whole exome sequencing or genotyping for individual mutations. You use HLA testing, which is also a genetic test. Now, every patient goes through multiple of these tests, combinations of these tests, and considerable amount of time is lost in each of these tests. And eventually, a clinician is going to get 3 different or 4 different reports from 4 different places, and the onus is on the clinician to make the consolidated understanding about the genetic test, which usually becomes very challenging, especially when 2 tests conflict with each other. Now, how can we avoid this? The avoidance is actually do a consolidated test, which today is possible by sequencing your genome from end to end. And by doing that, you can essentially combine all genetic tests that you want to ever do on that particular patient into one single test, making it very fast, very cheap, and very affordable. Now, we have done this now for multiple different cohorts. This is for cardiac channelopathies. Exomes give you around 34% positivity. By doing WGS for the exome negatives, you could add another 12 to 13% positivity. So in other words, from the positivity perspective, it increases the positivity around 40 to 50%. And we've done this across cohorts. I will not go deeper into it. Now, having said that, the real next big question to understand is what is really prevalent, right? And this becomes a very interesting scenario in practically every rare disease meeting. And every rare disease meeting typically would have a pediatrician, pediatric neurologist, you would have a medicine person, a cardiologist, right? And each of them will come and say that, I think this disorder is the most important, right? If you ask a pediatrician, they will say that muscular dystrophy is the most important. If a cardiologist, cardiomyopathy is the most important. If you ask a nephrologist will say chronic kidney disease is the most important. And there is never ever a consensus, right? Now, for years we have been trying to figure out, then somebody has to be right? It's not that everybody can have very different answers. Somebody has to be right. And that's when we ended up with this perspective that probably if everybody is wrong, right? See, in clinical settings, we should realize that in a clinician's perspective, the patient comes to you. And that's how modern medicine has been built. We teach clinicians to diagnose patients who come to you, right? So what you see is the subset of patients who actually come to you, and you make a diagnosis. And in experience, if you make a good diagnosis, more patients of the same kind come to you, right? And then we become an expert in it. And when you become an expert in it, your clinic is full of those patients that you see and you diagnose better. And therefore, you're right in your perspective. A cardiologist who does see cardiac myopathies, right, tend to see more cardiomyopathies because all his friends and relatives would refer that cardiomyopathies to him. And therefore, that becomes a very prevalent disease in his perspective or her perspective. In a similar way, a nephrologist would see a particular kind of disorder and so on and so forth. Now, what is the real reality and how do we really arrive at a reality? Right? To me, the only way to look at this reality is to sequence apparently normal people. Right? And the principle is very simple. If you have a genetic disorder, and typically a recessive genetic disorder, then you need to have two parents with two defective alleles to marry and produce an offspring so that you have a homozygous or a compound heterozygous genetic disease. Now, if you need to have that, then you need to have two parents with a heterozygous variant. Right? Now, if you apparently sequence normal people, right, given the probability of marriage practices within community, you can pretty much predict what is the chances, a random probability that two people with a carrier status can come together. In other words, allele frequencies in the general population is a very good estimate of what is going to happen in the clinic. Now, so that could estimate a prevalence in the genetic part of it. Now, if the clinician says that I don't see that disease, sorry. If the clinician says that I don't see that disease, that could be because of two reasons. One reason is that the patient does not reach the clinician. The second reason could be that the clinician does not recognize that patient has a disease. Or in other words, we will have a gap in the diagnosis, and the gap in the diagnosis therefore can be in hypothesis cleared by awareness education and enabling a diagnostic test. This is a hypothesis. Now, until 2019, this was a hypothesis because nobody could sequence people who are apparently normal, right? Because nobody would believe that sequencing apparently normal people is useful. So, in 2019, we got grants to sequence 1,000 odd apparently normal people, and what we found from that was even more remarkable. So, there is one example. This is from Kerala, from Calicut. That's where I studied. We found a large prevalence of individuals who came from northern Kerala for genetic variants associated with primary immunodeficiency disorders. And primary immunodeficiency disorders are a group of genetic disorders, today around 450 odd genes, and they have one defects in one of the pathways of the immune system. They could be frank immunodeficiency, they could be autoinflammatory, they could be a mix of them. And given the high prevalence, we decided to go back, work with my own professor, sort of create a very specialized clinic to sort of evaluate individuals who could fit into this paradigm. So, individuals who would fit into the paradigm would be people who come with sepsis, recurrent infections, failure to thrive, autoinflammatory conditions, undiagnosed immune disorders, systematically work up their clinical profile, systematically work up their genetic profile, and in 7 years, we have created a cohort of around 240 odd patients with diagnosed molecular immunodeficiencies. And today, there's a government program which sort of takes care of them in terms of giving IVIG free of cost, or offering them hematopoietic stem cell transplants, offering them a one-time payment. At this moment, it is largely done in Apollo in Chennai, but now that you have a program here, I'm sure you would also be able to get them. And a much more impact is that a larger number of family members could access now genetic counseling services, because these are very prevalent genetic disorders. Many of them were not aware that their child were lost because of primary immunodeficiency. Today, they have an option to go back and plan their family accordingly. And more importantly, we are today piloting a newborn screening program for primary immunodeficiency. The pilot is going to start early 2025. We plan to screen around 15,000 odd individuals with a prior assumption that this prevalence estimate is 1 in around 3,000 odd births. So, you can actually do this by going back to the clinicians, educating them, providing them the right kind of tools and tests, which is run in the medical college. It's not exome sequencing or genome sequencing anymore, because we know what is prevalent. We need to just provide that test that is prevalent for that community and actually implement the program in its entirety, helping a lot more patients. So, this is really possible. We have now many such examples of such cohorts. The second question that you would want to ask is, of course, we all know about newborn screening programs. And newborn screening programs are built on a very simple concept that there's a treatable genetic disorder that you can diagnose at birth, right? A biochemical test could offer the diagnosis, confirmation, and then offer the treatment. Now, the largest set of disorders which we use newborn screening for is for treatable causes of intellectual disability. There is no real consensus on what needs to be screened. In Kerala, we screen for approximately 6 genetic disorders. There were 7 genetic disorders, including PKU. PKU was dropped out. There are 6 genetic disorders today they are screened. But how do we know that the 6 are the right disorders to sort of look at? The answer is nobody really knows. Somebody made the test, therefore we are running the test. So we did this analysis to show that many of the disorders that we today run in newborn screening are probably not the right candidates to do. What we show is that, for example, ATP7B, which causes Wilson's disease, extremely high prevalence in the population, carrier frequency is approximately 1 in 80. We don't have a newborn screening program for that. Phenylketonuria, extremely prevalent in northern part of India, but not prevalent in southern part of India. Biotinase deficiency, there are extremely large prevalences in communities, much more than the western communities, but we don't have newborn screening programs for many of these. Now, this is the valuable opportunity that we lose, because these are treatable genetic conditions and treatable using a very affordable, accessible therapeutic today available. For example, Wilson's disease, it will cost probably 3,000 rupees to treat a Wilson's disease patient every month. The opportunity is lost because we don't diagnose them early enough, and we probably diagnose them too late enough to be able to treat them. Now, how can we really change this paradigm is the real point. Now, to change this paradigm, I think what we need to do is probably not really wait for a newborn screening program for Wilson's disease to be implemented, but actually take a much more pragmatic step to think that let us probably use genetic testing for infants who are sick, right? At least if they are sick in the early time period, the chances of getting a genetic diagnosis very early on is enormously large. Now, at least there's data from one RCT, not from India, but from the Kingsmore lab. What the RCT has shown is that for really sick kids, the genetic positivity could be as high as 46%. For sick kids, irrespective of whether you run a WGS or a WES, the genetic positivity is approximately around 20%. Now, just think about it. 1 in 5 of the sick newborns in NICUs could have a genetic diagnosis, and many of these genetic diagnoses could offer them a very accessible, affordable treatment, provided we do it, right? And to do it, of course, we need to convert it into a routine kind of test. Now, of course, when you talk about testing, people will talk about guidelines. Fortunately, now there are guidelines today from the ACMG FS IP chip. ACMG suggests for all developmental delay, intellectual disability and congenital abnormalities, either a WGS or a WES. IP chip suggests a first line test for all unexplained hypotonia cases, a WGS or a WES. And of course, I'm sure as clinicians, while you're all good clinicians and trained as good clinicians, you will always want to say that I will evaluate the phenotype of the child. At least in newborns, probably not a good idea. If the child is sick, irrespective of what phenotypes you have, it has absolutely no relation with the predictive positivity on the genotype. So probably a good idea would be to do it for a routine manner for all sick newborns, and of course the prior positivity is sort of a known number. Now, having said that, when we talk about genetics, and all that I talked about genetics is typically in the pediatric age group, because that is where we learn genetics, right? Genetics is a textbook in pediatrics. We don't have genetics taught in general medicine, for example, because you're not supposed to see genetic patients in adulthood because they're adults, right? They would have survived all genetic insults, they have survived, therefore they should not have a genetic disease. Now, that's really a big problem today, right? And the big problem today because almost all adult genetic disorders are missed out just because of the way we are taught genetics and medicine. For all of us, genetics ends with pediatrics, starts with pediatrics and ends with pediatrics. Beyond pediatrics, we really do not talk about a genetic condition. Now, if you look at, for example, endocrinology, one specialty, the genetic conditions could manifest at any point of time, right? It's not necessarily that you need to find the endocrinological disorder at birth. Absolutely not necessary. It could happen at any point of time. Some disorders are in puberty, some disorders are much later. For example, MODY is in middle age. So you could miss out many of these disorders if you don't really test out. You could look at, for example, chronic kidney disease. Now there is data to suggest that the yield is approximately around 9.9%. And in fact, for nephrology now, there are now guidelines have come up just because the yield of genetic testing in as simple things like chronic kidney disease is so large that last year, actually this year 2024, the NKF has actually brought out a guideline which now encompasses pretty much almost 50% of all CKD would fit into one of these. So that means that 50% of the CKD patients would today be eligible for a genetic testing, with the idea that this genetic testing could actually impact the management and the decisions to manage the patient going forward. In fact, for example, if you look at, there's also another study very recently, 2024, on donor kidney, and what they show is that 10% of the donor kidneys, because donor kidneys typically come from the extended family, would also have a genetic mutation. So essentially, you're going to transplant another kidney which is deceased already, right? And it is a double problem because the donor also has a disease, right? His kidney is also going to be abnormal, and the recipient is getting actually a subnormal kidney, which is also not going to function as efficiently. So as we do more sequencing, we also get to know more about these, and by getting to know more about these, eventually this ends up in the guidelines. For cardiologists out there, for example, cardiomyopathy today is covered, heart failure, in fact, unknown causes of heart failure and cardiomyopathies are covered under multiple different guidelines. Now there are some centers like, for example, the Mayo Clinic, which has a opt-out system for genetic testing. That means if any patient comes with cardiomyopathy or in fact heart failure unexplained, the EMR system automatically inserts the genetic testing. The clinician can of course click and opt it out, but by default the prescription is inserted by the system because the system knows that clinician could miss it out. They don't want to miss it out, therefore it gets inserted automatically. Now I'll move to the last part of my slide deck on what is really happening today. I've sort of simplified this, that cost of sequencing is reducing, throughput is improving, turnaround times are also improving subsequently, and we are probably the right spot in time today where genomics, which used to be a discovery tool, could now be used for routine clinical implementation. And going forward, there's going to be probably more routine implementation than more discoveries happening because the low-hanging fruit is probably all done, which can now be translated into routine clinical investigations. And when that happens, I think there's a small paradigm shift, I'll not say small, large paradigm shift that is going to happen. Today we use genetics as a tool to confirm the diagnosis. So assume that a patient comes to you, that means the patient has already have a disease. The clinician does his, of course, history, examination and labs, has a differential diagnosis, and genetics today is used to confirm the diagnosis, right? And of course, while confirming the diagnosis, it's already too late, as you would imagine, because the patient already has a disease, has found the right clinician, the clinician has done the diagnosis and is confirming the diagnosis. Now assume things in a different world. Assume that the patient does not come to you, right? Are you prepared for an eventuality where a patient can actually diagnose the condition or a clinician can diagnose the condition even without coming to you? In other words, the patient is apparently normal. I mean, this could include all of us. We're apparently normal, we are walking around, we don't have an apparent disease. But does it mean that we are perfectly normal? The answer is no. If you could diagnose apparently normal individuals, given the genetic variants, we could now triage them into risk groups to be able to manage them. In other words, you could start managing people even before they have the disease. Now, if you think that this is something out of the world, it is not out of the world. You already do this, right? And that's what we do in newborn screening. What we do in newborn screening is you have apparently normal newborns, you screen them for X number of conditions, and you say that you have this condition which is treatable. In other words, what I'm trying to say is, today all of clinical medicine that we do, that we learn, that we practice, starts with a patient with the signs and symptoms. In other words, signs and symptoms is where the needle is today, right? You don't get a patient who walks on the road saying that I think I have some abnormality, please check me, right? That doesn't really happen. In other words, we are restricted to that point when the signs and symptoms start. And most often, we get the patient much later than this, right? But a real value of doing all that we do is when we can shift this needle to the left. Or in other words, can we identify people with a biological abnormality, a molecular abnormality that is treatable, and treat before the disease occurs or before the signs and symptoms come. In other words, actually can you prevent signs and symptoms occurring in an individual by looking at a basal molecular defect. And that would necessarily mean that you need to convert this into a risk assessment or a screening paradigm. Now, of course, newborn screening I did talk about. The best newborn screening programs in the world, for example, in the US, looks for 37 genetic disorders. And it costs $100 odd to test every newborn in the US. And even in the US, not all states cover all the 37. Different states cover different numbers of genes and disorders. And today we know from large-scale programs what is the positivity is approximately 1 in 300 to 500 newborns, depending upon what gene list and what test you pick up. Now, newborn screening is for treatable genetic disorders. So that means that every 1 in 300, 1 in 400 children born would have a treatable disorder, which is treatable by their healthcare system. Now, the apparent question then would be, can we now change this? Right? 37 is a too small number. Today we have around 150 odd genetic disorders which are treatable. But to do 150 odd genetic disorders to be treated, then you need to change the paradigm for newborn screening. And a lot of countries, a lot of programs around the world are trying to do this. And the approach is very simple. Can we sequence a newborn? Right? Once you sequence a newborn, you can have the entire genetic makeup of the individual. And then you can look for diseases which are prevalent, penetrant, high actionability, and treatable with an affordable, accessible therapeutic. Now, each of this is going to be very different in different parts of the world, right? And therefore, there is never going to be a newborn screening test that is applicable to even an entire country like India. Because even in a country like India, there are different populations which have very different genetic diseases which are prevalent. Now, there is not enough ecosystem to be building such individualized newborn screening programs, getting it validated, putting into the program. That's never going to happen. A probably more pragmatic approach would be to sequence and then decide for that population what should I report. Right? Now, how do we really reach here? And the way to reach here is, of course, look at the numbers. The estimated numbers, if you run a newborn screening program using genomic sequencing, is approximately 1 in 182 for treatable disorders. And in many ways, this is an underestimate because we today do not know all genetic variations which could cause a disease. Right? We only know a subset of disorders and subset of variants on the disorders. So this indeed is a very small underestimate. But nevertheless, if you look at the numbers, you will see that this is pretty much doubled the yield of a newborn screening program without changing the price of a newborn screening program. Right? Now, of course, now that people have started doing this, there is data, and this is from few months ago, I think from October, published in JAMA. This is from a large program called Guardian, which sequenced around 4,000 odd newborns from diverse ethnic groups in the US. And what they show is that the screen positivity rate is almost 10 times that we sort of estimated to be approximately 3.7%. That means 1 in every probably 35 odd children, 30 odd children would have a medically actionable insight if you sequence them at birth. And this indeed is an extremely large number, and this is the highest number that we have arrived at in any one of these studies. And this, I think, is going to change the way we look at newborn screening, because there is no other study, no other panel anywhere in the world which can arrive at a 3.7% test positivity of apparently normal newborns at birth. Right? Now, that is also a number that you should keep in your mind, that is an opportunity lost for newborns if you don't do it. So we plan to sort of start this from scratch. And to start from scratch, what you need to do is to understand what are the genes and what are the therapeutics which are affordable and accessible in India. Because this is a different number in different populations. In India, we know what is affordable, accessible, and what is permitted. They're not all of 150 odd genetic disorders are treatable in India because many of those treatments are unaffordable. Now, in a newborn screening program, the part that we need to keep in mind is that we should never be in a position to inform the parents that you have a child with a genetic disorder which is not treatable. That to me is criminal. Right? It's only going to worsen the status quo. It's not going to make it better. What you need to inform the patient is that you have a treatable genetic disorder and your healthcare system is able to treat it. That means you need to have an accessible, affordable therapeutic and for a penetrant and highly prevalent genetic disorder. Right? Wilson's disease, for example, would fall into that category today. But today, unfortunately, there is no Wilson's programs anywhere in the world, though it is very prevalent, for example, in India and China. There's no way we are going to get a newborn screening program implemented. The only way probably would be to sidestep in technology to be able to do a broader panel, but inform what is actionable in that particular population. Now, moving back to the needle, and what I all talked about is patients who come to the clinic. Now, is genomics then applicable to patients who don't come to the clinic? The kind of people whom I talked about are walking on the road. Would they benefit from genomics? Right? I'm sure they would have different opinion. But the real fact is that it indeed could benefit people walking on the road. And the insight actually came from our 1000 odd genome program. And what we really found was there are some genetic disorders which are extremely prevalent in the population and are also very unlikely to be diagnosed by the healthcare system. The first of it is cardiac channelopathies. These are essentially sodium-potassium channel mutations. What we estimate the prevalence is approximately 1.4%, probably highest in the world. The next highest is in a consanguineous community in Qatar, is approximately 1.2%. But just look at the numbers, it would necessarily mean that 1 crore Indians do have a gene mutation which could predispose them to cardiac arrhythmias, treatable genetic condition. Second is familial hypercholesterolemia. I'm sure if there are biochemists in here, they would be doing LDL cholesterol levels. They will all be reporting it as high risk cholesterol, not realizing the fact that a significant number of them are actually genetic disorder which runs in families, which can be treated with a very effective drug, which is statins. And for that matter, with genomic studies, we have also shown that the statin pharmacogenomics is also very prevalent in India. At least 10% of individuals would require to change over from statins to another lipid lowering drug, and around 30% of individuals would require to have a dosage modification for the statins. And of course, when you talk about dosage modification, about pharmacogenomics, there are many more conditions which are extremely prevalent. For example, abacavir, 4% of them would have an HLA-B27, HLA-B57. We have carbamazepine around 3%, allopurinol around 3.7% widely used drugs in the population. And everybody whom we have sequenced is an approximate average 8 actionable pharmacogenomic variants. Of course, this will not cause a disease, but this will only cause a trouble when you get the right drug at the right point in time. So put together numbers, we have a fairly good estimate of how much it would benefit a normal individual walking on the road. This is 1 in 20. To put numbers, around 2% of them would have a hereditary high prevalence, high penetrant cancer susceptibility gene. 1% alone is BRCA1, BRCA2, and the 0.5% is PALB2. The rest 0.5% to 1% is the colorectal cancer genes. In terms of cardiovascular diseases, you have 3 disorders, each of them approximately running in around 1%: familial hypercholesterolemia, canalic channelopathies, and cardiomyopathy. So put together, all of these very prevalent genetic disorders would affect approximately 1 in 20. These are preventable, treatable genetic disorders. So before I close, my last slide is to say that therefore genomics has to be looked in different perspective, different lenses at different points in time. You could of course start with a newborn screening program looking at treatable disorders which are immediately treatable and manageable. much later and different points in life, you would want to use it for different kinds of things. In childhood, you would want to look for example, autism spectrum disorders. Early adulthood, you would want to look for example, MODY. You would want to look for hereditary cancers. You would want to look for pharmacogenomics as you get more treatments. And eventually, you would want to also look at now increasingly treatable genetic conditions, including Alzheimer's and Parkinson's. The genome is constant from the day you're born to the day you're dead. But the way you could use your genomes are going to be very different at different points in times with very different kinds of perspectives. I think I'll stop there with some take-home points. And take-home point number one is genomic sequencing is becoming more affordable for routine clinical implementation and even beyond routine clinical implementation in non-clinical settings for apparently normal individuals. At an individual level, this could afford a disease diagnosis, and at a population level could provide very useful insights or data for public health implementation. Genetic diseases are not rare. We should not call them rare anymore. The cumulative prevalence is approximately 1 in 10. And therefore, genomics is for everyone, and genomic evidence is for a lifetime. Thank you very much.
I think now we can have some questions. I'll just start it off with Dr. Vinod. So there is a set of patients who come to us from abroad saying that they like to screen. Why is it that it is not allowed in children outside? And is it a problem to make it so accessible?
Yes.
Particularly the UK, I think.
No, so different countries have different social, economical restrictions on doing some things. Like for example, in India, prenatal testing is illegal, right? Sex determination is illegal as a prenatal test. But for example, in the Middle East, sex determination is not illegal, right? In fact, the Middle Eastern countries, like for example, Dubai, UAE largely, has just started in October mandatory universal whole genome sequencing for all marriageable age group individuals. That means you cannot get married without doing a whole genome sequencing. Simple. Now, I'm not joking. This is a reality. Right? You cannot get married in UAE if you don't have a genome. See, that is because today they have evidence to suggest, and they have proven track record. UAE used to be the thalassemia capital of the world. They used to have so much thalassemics that their entire healthcare system used to be clogged with thalassemics. In a decade's time, by offering universal HBB genotyping, they have eliminated new births with thalassemia. Right? From 2020, they have 0 births with thalassemia. Right? Not by changing marriage practice. Marriage practice is something that is social. Right? You don't decide somebody to marry or not marry depending on whether you're a carrier or not carrier. But what happens after the marriage is something that the family can plan with the evidence at hand, right? By offering counseling to practically everybody in that age group, they could eliminate a genetic disease in totality. Now, that track record now tells them that we could now do much better. Because of a consanguineous practice of marriage, the point is not to change the consanguineous practice of marriage. That is going to stay. Right? Not forever, but at least for a foreseeable time. But the question is, how do we change the clinical outcomes by using technology at the right point of time? Right? Now, different countries have different ways of looking at it. I'm sure you're following the laws in the US. Right? Some places do have crazy laws. Right? So, people who can afford will go and get it done. Right? And that's the way it is. It's not that, I mean, don't be under any assumption that people don't travel the other way around to get, for example, sex determination. Right? That's a reality. Right? People do travel to UAE for sex determination because it's legal there.
That's a wonderful talk. Thank you very much for the information. Just recently, one child with congenital septal hypertrophy of the intraventricular septal hypertrophy. That's very rarely reported from the biology literature. Only 4 or 5 cases reported. So this particular aneurysm, intraventricular septal aneurysm. So ultimately, this final answer
So I'll answer the last question first, right? What happens if somebody else has access to your data, right? Can they mess up your life? I mean, my simple answer to that, of course, out of jest, don't take it seriously. We already mess up our lives based on what is there in the stars, right? Genetics cannot do anything worse than that, right? I mean, my obvious question that comes from the audience is that what will happen to marriages? I think the marriages are already messed up because of the stars, right? If you're messing up for a scientific reason, I think that is still valid, right? So that's the answer to the last question. Then I'll go to the first question, that we should always realize that genetic testing is not just about the clinical outcomes, right? In most cases, what the patients in the family is requiring is a closure. You may not have a treatable genetic condition. That's perfectly fine, right? Like the family who wanted euthanasia, it's not that they're in any hope that the child will have a treatment, right? They know the child does not have a treatment. They're seeing the child dying in front of them. What they want is to have a closure on why is this happening, right? And that why will allow them to plan the next pregnancy. And I've shown an example where that answering that why could plan the next pregnancy and then could have perfectly normal children. So I think we need to go beyond the clinical outcome paradigms to actually understand what does the parent and the family want. And in most cases, what the parent and family want is a closure, right? In fact, they have spent much more money going to temples, churches, mosques, and holy places, trying to find a cure or trying to find a closure to the problem. As scientific people, what we should enable is to have a scientific way to close the problem, not really keep it open-ended so that they go helter-skelter and eventually do something else. And I missed your second question. I don't think it will create any difference in the clinical outcome, right? But if you find a genetic mutation that will allow the family in an extended way, right? For the child, it may not make any difference because you will anyway do the surgery.
Transplantation is our only option.
Your second question, please.
Pharmacogenomics.
Pharmacogenomics.
The drug interactions and
Right.
common.
Now, the problem with pharmacogenomics is typically that the test has to be done before you administer the drug. And in most cases, you don't have the time window to hold the drug before the test is being done. Only in the major centers, you have an in-house capacity to do centers. Large oncology centers in the US do have that, where you have a 2-day, 3-day turnaround time. But in most cases, that is not really possible, right? Especially if you don't have your own center. But if you have your own center, very good. If you don't have your center, I think the way to consolidate testing is the way to go. And this is what we have been sort of talking about. You might have been doing genetic testing to find a genetic mutation for an X condition, but pharmacogenomics can now be included as part and parcel of it. And by doing that, you can actually get a much faster turnaround time.
So individualization of drug treatment for a particular person also can be.
Yeah, absolutely. So the pharmacogenomics is all about that, because essentially there are very few genes that metabolizes all the drugs that we take, and many of them, like for example 2C19 or 2D6, essentially metabolizes almost 30% of all the drugs. So if you have a mutation, it's going to affect multiple different drugs. Yeah. And therefore testing is mandated. They are in the guidelines. Nobody follows them because we don't have a solution to get it in a turnaround time. Yes, sir.
Thank you for that excellent talk. Even I could understand a bit of it. You came down to other. Thank you very much. I have 3 questions, Vinod. First one is, would you put yourself in my position and answer the question, what is it that believers can do with all that has been happening today? Number 1. Number 2, what is it that you think that we should start off with, especially with Chelsea so excited? High time we had a center of excellence, so genomics is the way forward. And number 3 is all about, you gave us a lot of examples. So, you know something about what we should concentrate on.
Yeah. Now, answer to the first question, what should, as believers, as an educational institution, a premier center for healthcare do? The answer to that is be example for others. Right? Be example for others. Because the data that you generate is probably going to be the first of its kind just because of the unique ecosystem Kerala has. Right? I will not probably suggest in any other state, because Kerala has a very unique ecosystem. First is the per capita GDP of Kerala is almost thrice that of national average. Right? Second, patients are very aware. They are also able to comprehend the implications of the genetic testing in many aspects. And you have a very robust healthcare system in the state, which can sort of create and accelerate all what we do. What is missing is the initial proof of principles, right? While we all tend to follow the guidelines from the West, we still do not have numbers of what is really in our place. And that is possible only if you do it, right? And the best example is, of course, from Dr. Chepsi, right? There are many disorders that we never thought were prevalent, right? But we see it recurrent. It may or may not be associated with the condition that you tested for. But for example, we know heterospherocytosis is extremely prevalent, right? I mean, I've never seen a paper from heterospherocytosis from this part of the country. But we know it is extremely prevalent, just as an incidental finding in practically almost every 1 in every 30 or 1 in every 40 reports has a heterospherocytosis incidental variant. Now this is important because if you have heterospherocytosis, then you can have an extended family screen, you can treat, you can do community screening, community awareness, and the management accordingly. Right? Management essentially means that avoid some kinds of drugs and also have a healthy lifestyle. Now, until you provide this data, right, nobody else is going to create it for us. An American is not going to create a data for us to say that now you do heterospherocytosis testing. No, that's not never going to happen. We have our problems to solve. Our problems are unique. If we do it, we provide the data in terms of publications, conferences, awareness, education. The rest of the people will follow. And as an Apex center, I think it is our responsibility to the community to be able to do that. Right? If we don't do it, nobody else will do it. Dr. Chepsi has now today created probably one of the largest cohorts of its kind of a disease spectrum, probably in the country. I have not seen a larger series cohort. And even that in one single year. Right? It's not like a 5-year, 10-year cohort. It's like a 1-year cohort, and it's growing. And so that necessarily means that if we do it in a very systematic way, we can build global cohorts and be leaders in it. And these are disorders where we have, this is our problem, right? If we don't become leaders, if we don't create our guidelines, who else is create for it? Right? Your second question, sir?
Second question is, with all that is available now, and I'll also add one more little thing. You worked a lot with Dave, obviously. How did you get those clinicians to get excited? I'm not able to get my clinicians to get excited about this. And partly saying it's anyway too expensive and we can't get it. So how do you, what would you do?
So the answer is very simple, right? All collaborations happen when you take one step back, right? So all the publications that we had from Guardian, right? It's not just one publication that is shown. We have close to around 80 publications in the 8 years that we ran. There is no one single publication where the clinician is not the first author, right? Which doesn't really happen in collaborations. In collaborations, typically you first start talking about where am I in the order, right? Some ethical committees even insist that you need to decide on the authorship list before I give the ethical clearance. By taking that step back to say that it's your patient, it's your clinic, you take the first authorship, right, is to me the reason why it worked. Because there was no other system, I mean, I've not seen an example anywhere else where a research organization and a research grant, where somebody has actually fought to get the grant, has come and say that you take the first authorship, right? Now by doing that, we could quickly improve the scale. By improving the scale, we could actually benefit many more people, right? So sometimes taking a step back and saying that you take the credits is going to probably do more to the system and the entire system, right, put together. It's not that only the clinician benefited, the patient benefited, we benefited, everybody else in the system benefited. So I think that could be one of the ways to go. And especially when you're setting up multi-center cohorts, that setting that policy beforehand might actually become very useful, so that there is no confusion going forward.
So regarding that cost, I think our partnership with them, the costs are also probably half of what is there in the otherwise with the competition. In fact, it was even lesser. In between it went up, but still for at least neonatology at least, which they usually do exomes, it would be much more than, and the benefit what we have, like he said, some of the things we have not expected out of the report and it comes up. And it gives you a chance to inform. Now, whether it will affect the patient or not, like one of those cases which I was mentioning to him, that child had a particular syndrome which was not diagnosed for a long time, had multiple physical disabilities. Family is moving from pillar to post, trying to find out what is the problem. They go to some specialist or the other. Here, by chance, they happen to have a thrombocytopenia which got settled. But somehow they came to our lab, and then because this collaboration was there, we sent in the sample and it was diagnosed with a particular syndrome. How it helped that family was, okay, now we know that they have a disease, even though we were not going to correct it. Second, it opened up an avenue of certifying their amount of disability, which opens a window of support from the government system which exists. So the government also is hesitant to do it unless you show proof. Even though I cannot write that letter, I can send that report saying that this is it. And they were able to, at least for the rest of their treatment, they will have some kind of financial support. So it might not help the way we want them to be helped, but I think there is some sort of help at all points.
You know, we looked at genomics in a big way. Vinod might be sitting there was the team came at that. But we found it's far too expensive for us at this point in time. Is there some guidelines you can give us where to go, how to go? I know our unit in CMC has really struggled. Sunita Nanda has had a real rough time, but she's getting there somewhere. Is there some advice you can
Yeah,
give us?
the best advice I can say is, if you actually do more, if you actually do more, it becomes cheap, right? Now, genomics is what you call a specialty by itself, right? Don't underestimate that you can buy a machine and you can start doing it. It is like any other super specialty, requires complex, multiple people to come together to execute it. And for single hospitals to do it at this point in time, right, might not be cost efficient. So it is like a CT scanner. 20 years ago, I'm sure you would appreciate, it was costly, right? Very few centers could do it. But eventually, as the ecosystem grows, you will be able to imbibe it in-house. I've also brought in Swaroop, who is a national sales head, very specifically to answer your question about prices, right? See, prices are always something that is very, what you call, subjective, right? And that is subjectiveness in the sense that what is the value that you attach to it. In terms of our throughput, in terms of our technical capability, we can offer the best prices possible just because we have a high throughput system. But I think beyond the price that we want to offer is not just exome sequencing, but the interactions that will enrich both of us, right? While Dr. Chepsey says that he has found a lot more, the reality is that we also learned quite a lot more, right? So I think that interaction and collaboration is something that will accelerate this space.
So we just hope that you keep coming all the time.
Sure.
Maybe one more question from there.
From a psychiatrist perspective, the genetic testing is not routinely done for the memory disorders. So is it ethical? For example, if I have a patient who is having depressive symptoms in over 65, they suspect that this is going to be Alzheimer's dementia. So there are some genes which say that this could be this. So diagnosing it a little bit early might give clinical benefit to the patient
quick answer to that is, to me, very simple, right? There are already guidelines on who should be tested. At least in psychiatry, the guidelines today for genetic testing is largely in the pharmacogenomics part of it. Right? There are already guidelines, it is mandated to be tested. Now, when you already do that test, the additional germline cost testing is not going to add significantly large amount of money, right? So in that perspective, when you look at it, when there is already a guideline, you are supposed to do this, and that additional test is not going to add 2x, right? That becomes a viable solution and viable option. And one of the things that we were discussing in the morning is that Wilson's disease I sort of talked about, right? Have anybody seen the first Wilson's disease paper that was published by Wilson? Right? No. We all are clinicians, we have all learned pediatrics. Wilson's disease is hepatocellular degeneration, hepatomegaly, splenomegaly with jaundice, with some eye signs, pediatrics, and this is Potter, right? Have you ever seen an adult Wilson's patient? Right? Plenty. So that's reality, right? We actually see more adults than in children. Now think of it, this is a treatable genetic condition, right? We should have treated them very early on. Right? In India, that's a reality. We even have a medical student who collapsed and died out of Wilson's disease. Think of it, medical student who could not, with all the signs and symptoms, could not diagnose his Wilson's disease. Right? It's because of our very focused way of education. Right? Never in my medicine rounds I have ever seen my professor talk about Wilson's disease. But you cannot pass pediatrics without diagnosing Wilson's disease. So I think that's the problem. So our presentations of some diseases are extremely very different. Like for example, cystic fibrosis. Our prominent presentation of cystic fibrosis is not pulmonary. It's actually infertile. Right? 1% of infertile males actually have cystic fibrosis.
So, as a genome expert, what is your take on this gene editing tools in terms of precision medicine? Because if you browse around, you can see many CRISPR-Cas9 technology for so-and-so cancer and all. And many Western hospitals are actually putting this term in their website, CRISPR-Cas9 technology-based therapy. So what is your take? Like, is that really possible in Indian setup?
See, genetic editing, CRISPR-Cas is one of the tools for genetic editing. Genetic editing has a lot of tools. And in fact, many of these tools are going out of patent and therefore likely to be democratized. Like all the small molecules, biologicals that we use are likely to be democratized. And to give examples, the best example is the CAR T therapy. Right? It is essentially genome editing of a T cell. We are 1/10 of the global cost, right? And that cost is even going down as they go out of patent. The point to note is that we need to start to be able to do it. Right? We cannot sit on the sidelines and think that somebody else will make it cheaper for us. That's never going to happen. Eventually, a significant number of genetic diseases would become treatable. I'm not saying all, a significant number would become treatable with one of the genome editing tools. Because of the modular way it works, you can actually, sort of use the tool without having to go through an extensive clinical trial, which in US, which widely called as an N = 1 clinical trial, means that you have an extremely rare disorder, a commonly used tool, but modular. You can modify it and use in one patient, and that's pretty much, that's only one patient in the world. So there's no point in a clinical trial.